In this video, we're going to talk about series circuits, so about how we can arrange more than just one component. So before, we looked at examples of, say, just a battery connected to a single resistor. And now we're going to look at how can we combine more things together. So there's different ways to arrange them, and the first that we're going to talk about is in series. So elements are considered in series. This can be batteries, this can be resistors, this can be any sorts of things, if the current must travel through both elements. So two things are in series if current has to flow through one and then the other. So some examples of this: if I've got a resistor and then another resistor, those are in series. If I've got a resistor and then it bends and then I've got another resistor, those are also in series. There's only so many ways you can do it. Things that would not be in series would be something like this. These two right here would not be in series because the current's going to go through one or the other. However, this first one and the top one are in series because the current flows through. If it goes along this path, it must go through both. The bottom two are also in series because if it goes through this path, it must go through both. However, it does not have to go through both the top and the bottom. In fact, it can't go through both the top and the bottom. So those would not be in series. So if resistors are in series, the current flowing through both must be the same. So charge has no other options, so it must be constant. So if you've got a single wire and everything's along that wire, whatever charge is flowing through it has to flow through everything. And so there's nowhere for it to branch off and split and for you to lose that. This is where we think about that water example. If you've got a pipe of water and it's going through a bunch of things, every place the water has to be moving at the same speed with the same amount of water has to be moving. Otherwise the pipe would explode, right? Because you'd get a buildup of water in one place. Or the pipe would just randomly be emptying somewhere because water's moving faster after than it's coming in. And that just doesn't make sense. So when you've got elements in series, the current must be constant everywhere. The total resistance is calculated by adding all the resistors together. So in other words, the total resistance is R1 plus R2 plus R3 all the way up to however many R's you have. So you can imagine that instead of having, if you need to have 4 ohms of resistance, you can either put two 2-ohm resistors in series so that the total resistance in that section is 4, or you can put a 1 and a 3, or you can put just a 4, but that's what we're talking about here, is that we can find the total or equivalent resistance by just adding the resistors together. And the total voltage drop is likewise the sum of the individual voltage drops. So the total voltage change is V1 plus V2 plus V3 plus Vn. So let's look at an example, and that'll kind of show you where we think of these through. And these can be used to find equivalent resistance, which I had mentioned earlier. And that means we can simplify our ideas of circuits by replacing we can simplify a circuit by replacing a bunch of individual resistors with one resistor of equivalent resistance. Let's look at an example, and that'll help illustrate that idea. So in the left circuit below, suppose the voltage of the battery is 12 volts and the resistances are R1 is 1 ohm, R2 is 6 ohms, R3 is 13 ohms. What's the equivalent resistance? So in other words, if instead of having these 3 resistors, I want to just have one resistor and have the same current flowing through this, have the same effect on the battery, what would that one have to be? Well, we know that the equivalent resistance is just the total resistance, which is going to be R1 plus R2 plus R3. That's what we said on the previous slide. Just add them together. So that will be 1 ohm plus 6 ohms plus 13 ohms. And that will give me 20 ohms as my equivalent resistance. So in other words, if instead of having a 1 ohm, 6 ohm, and 13 ohm resistor in series, I could replace them with a 20 ohm resistor and the circuit would behave exactly the same. Now it's asking what's the current through the circuit. Well, we know that V equals IR. So in other words, V over R is equal to I. Now we can't do that easily for R1 because we don't know the voltage drop across R1. We don't know this V. We don't know the voltage drop across R2. We don't know the voltage drop across R3. But we can jump over to the second one, and we said they behave the same, and we do know that if it goes up by 12 volts here, if we think about our water example, if we have a pump that moves it up by 12 volts, and then it goes through one waterfall, then this waterfall has to come down by 12 volts. So in other words, the voltage here has to be 12 volts in this equivalent resistor, and we have to have whatever the equivalent resistance. So I in the current is equal to 12 volts divided by 20 ohms, which is going to give us, what, 6/10, 3/5 of an amp. Now, if we want to test this to show why this works, well, now we know 3/5 of an amp is going through each of these resistors because the current has to be the same at every point in this circuit because it's in series, right? The water has to flow through. So let's go back to our water example, and instead of having just the one waterfall, now let's do the 3 waterfalls. So going through each of those resistors and having a drop on each. Well, through the first resistor, R1, it's going to have a voltage drop of 3/5 times 1 ohm. So it's going to have 3/5 of a volt drop. In the second one, we're going to have 3/5 times 6. So that's going to be, what, 18 over 5 volts. And in the third one, we're going to have 39 over 5 volts. And if we add all those up together, 3 plus 18 is 21. 21 plus 39, that gives me 60 over 5 volts, which simplifies to 12. So that's what we're seeing here, is that we can basically we can simplify it into a simple circuit, find the math, and then we can go back and find out all the individual pieces if we want. Now, it didn't ask for that in this case. I was just showing that to kind of prove it and justify why these are connected. Second example here, in the figure, in the circuit shown below, there are 3 resistors of known value and a third, that should be a fourth, which is unknown R3. Given that the equivalent resistance for the entire circuit is 150 ohms, what's the resistance of R3? So if we know that RT is equal to R1 plus R2 plus R3 plus R4, and we knew RT, we know R1, R2, and R4, we can write that R3 is equal to RT minus R1 minus R2 minus R4, which in other words is 150 ohms minus 10 ohms minus 25 ohms minus 15 ohms. 25 plus 15 is 40. 40 plus 10 is 50, so that means R3 is 100 ohms. And then if we knew the current in the battery, or the voltage in the battery, we knew the current through the circuit, we could find the voltage in the battery, and there's all sorts of things you can use Ohm's law to calculate from this point. This is one that'll take some practice getting used to and playing around with, but of course if you have questions, please ask.